path recirculation systems are dual duct systems that use a single supply fan, constant volume reheat systems, and multi-zone systems. The single duct VAV system that we're using for our example has a single recirculation air path. Again, all the air supplied to each zone is a mixture of outdoor air and centralized recirculated air. As John explained earlier, Standard 62 gives you credit for the unused or excess outdoor air that recirculates from non-critical zones. In a system with a secondary recirculation path, some of the air supplied to each zone is recirculated from other zones without directly mixing with first pass outdoor air from the intake. For example, fan-powered VAV systems use VAV terminals that recirculate air from the ceiling plenum. And two-fan dual-duct VAV systems recirculate air from all zones through both the heating air handler and the cooling air handler. In a series fan-powered VAV system, one air handler brings in outdoor air at a central location and mixes it with air recirculated from all zones before delivering it as primary air to all zones. In addition, each VAV box recirculates air from the ceiling plenum, providing a secondary recirculation air path. Standard 62 calculations result in a credit for excess unused outdoor air in the recirculated air, whether that recirculation occurs centrally or locally. In a dual fan, dual duct system, the cooling air handler brings in outdoor air at a central location and mixes it with recirculated air from all the zones before delivering it down the cold duct. The heating air handler conditions only recirculated air before delivering it down the hot duct. Both of these air streams contain some excess outdoor air that has been recirculated from overventilated zones. So the calculations in Appendix A give you credit for this. Now, we're not taking time during today's program to walk through the steps for calculating zone ventilation efficiency for systems with more than one recirculation path. However, we did record that content, so you can review it at another time if you like. You can find it as supplemental material on the DVD or view it on demand at our website.
Okay, getting back to our example. Step 3B for this system is easy because it only has a single recirculation path. So the equation for zone ventilation efficiency is 1 plus X sub S minus Z sub PZ. We just calculated X sub S to be 0.17, and we calculated Z sub PZ for each zone earlier. So solving this equation, we find that the zone ventilation efficiencies vary from 0.71 in zone 1 down to 0.67 in zone 3. Step 3C is to find system ventilation efficiency, which is simply the worst case or lowest zone ventilation efficiency. For our example, that's 0.67, the ventilation efficiency for zone 3. Okay, we're almost there. Now, with system ventilation efficiency calculated, the final step, step 4, is to calculate the required system outdoor air intake flow, or V sub OT. This is calculated by dividing the uncorrected outdoor air intake, which we found earlier to be 1,000 CFM, by the system ventilation efficiency. So for our calculated efficiency of 0.67, the required outdoor air intake for our example system is 1,490 CFM. That is, in order to deliver 500 CFM of outdoor air to zone 3, which is the critical zone, Standard 62 requires bringing in 1,490 CFM at the air handler. Zones 1 and 2 will be overventilated at this condition, receiving more outdoor air than the standard requires. Now that we've calculated system ventilation efficiency and intake airflow using Appendix A, let's look at the default method using the lookup table in the standard. As I explained earlier, you can use either Table 6-3 or Appendix A to determine system ventilation efficiency. Outside of Step 3, however, all the other steps are unchanged. Here's an excerpt from Table 6-3. It lists the default values for system ventilation efficiency based on the largest zone outdoor air fraction, Z sub PZ. For our 3-zone example, recall that the largest zone fraction was 0.5. By interpolating in this table, we find system ventilation efficiency to be 0.65. Note that example 6-J in the standard 62.1 user's manual clarifies that interpolation is allowed when using this table. And it's worthwhile doing because it results in a higher value for system ventilation efficiency. But one important thing to notice about this table: if the largest zone outdoor air fraction is greater than 0.55, standard 62 requires you to use the calculation method in Appendix A. For our example, using the default value of 0.65 for system ventilation efficiency, the required outdoor air intake would be 1,540 CFM. So in this case, using the calculations in Appendix A resulted in a system intake airflow that is less than what would have been required if we used the default from the table. Note that the default values in Table 6-3 assume an average outdoor air fraction, X sub S, of 0.15. So for systems with a higher average fraction, like our example, using Appendix A will result in a higher system ventilation efficiency and a lower intake airflow. I mentioned earlier that I would discuss the impact of heating mode versus cooling mode. As Paul explained, when delivering warm air to the zone, some configurations have a zone air distribution effectiveness less than 1. So we used our same example to see how an effectiveness of 0.8 would impact the system intake airflow. An E sub Z of 0.8 during the heating mode results in a higher zone outdoor airflow, and therefore a higher outdoor air fraction. In our example, the worst case fraction increases to 0.63 compared to 0.5 in the cooling mode. With this high fraction, Table 6-3 cannot be used. So using Appendix A, we find that even though the zone outdoor fractions are higher, X sub S is also higher because the system primary airflow is lower. In our example, this results in a higher system ventilation efficiency and a lower intake airflow. I calculated the outdoor air intake to be 1,300 CFM during the heating mode, compared to 1,490 CFM in the cooling mode. But it's really hard to generalize this for all applications, so it depends on what the system primary airflow is when the zones are in heating. And of course, if the system is designed so that zone air distribution effectiveness is 1 when heating, this comparison isn't even an issue. By now, after all these calculations, you may be thinking that you should create a spreadsheet to save some time in your next design. Well, ASHRAE thought the same thing, and they include a spreadsheet tool when you purchase the standard 62.1 user's manual. So you don't need to create your own unless you really want to. In addition, the ventilation rate procedure calculations have been built into TRACE 700. So if you use this tool for load calculations, you've already entered the zone level detail needed to calculate zone outdoor airflows. And with just a few more inputs, it can perform the system ventilation calculations too. To wrap up this section on system calculations, let's compare the calculated intake airflows for all 3 system categories listed in the ventilation rate procedure. For our example 3-zone building, the individual single-zone systems deliver 300, 400, and 500 CFM respectively, for a total of 1,200 CFM for the overall building. The 100% outdoor air system delivers 1,200 CFM to the building also. And the single-path VAV system delivers 1,490 CFM. Although we did not go through it during the program, as Dennis mentioned, we did record a supplement during which we walked through the same example for a Series Fan-Powered VAV System. As you can see, the impact of ASHRAE 62 giving credit for unused outdoor air in a secondary recirculation path can be significant, reducing the intake airflow in this example to 1,180 CFM. Now, I think it's worthwhile to point out that to compare the performance of these different ventilation systems, you need to focus your attention on the calculated intake airflows, V sub OT, not on system ventilation efficiency. The reason I say this is that many people erroneously think that a dedicated outdoor air system has 100% ventilation efficiency. Based on that, you would conclude that a dedicated outdoor system brings in 33% less outdoor air than the single-path VAV system, since its ventilation efficiency is 67%, and 15% less than the Series Fan-Powered system. But when you compare the calculated intake airflows, 1200 CFM versus 1490 for the single-path VAV, the difference is only 19% for this example, not 33%. An intake airflow for the Series Fan-Powered VAV is actually a little less than for the dedicated outdoor system, not more. Why the difference? Well, it's because ventilation efficiency of a dedicated outdoor system is usually less than 100%, but it's just not necessary to calculate it as part of the ventilation rate procedure. As defined by Standard 62, system ventilation efficiency is the sum of the outdoor airflows required in all the breathing zones, V sub OU, divided by the outdoor airflow that enters through the system level intake, V sub OT. For most dedicated outdoor air systems, the intake airflow is equal to the sum of the zone outdoor airflows, each of which is based on peak zone population, with no credit for system-wide population diversity. As a result, system intake airflow is based on all zones being at peak population simultaneously, even though that's typically not the case. So for our three-zone example, the required outdoor intake flow is 1200 CFM when using a dedicated outdoor air system. Remember that the uncorrected outdoor air intake for our example building was calculated to be 1000 CFM. Therefore, the ventilation efficiency for this dedicated outdoor air system is actually 83%. While we're on this topic, what about single-zone systems? When you just look at each system individually, system ventilation efficiency is 100%. But if you're comparing the use of three separate single-zone systems to 100% outdoor air or a multiple-zone system, you really should look at the overall building when making the comparison. For our three-zone example, the total outdoor air intake flow for these three systems is 1200 CFM. Again, with an uncorrected outdoor air intake of 1000 CFM for this building, the combined system ventilation efficiency is 83% when using single-zone systems. So when comparing the performance of these different ventilation systems, you need to compare the calculated intake airflows, not system ventilation efficiency. Even though ventilation efficiency is typically not 100% for these other systems, it's not calculated as part of the ventilation rate procedure in ASHRAE 62.
So that completes our step-by-step walkthrough of the ventilation rate procedure calculations when designing a system. Before we move on to discuss how to control the system during operation, let's briefly discuss the exhaust system. Paul?
Through a recent addendum, the exhaust airflow requirements were moved to a separate section, Section 6.5, since they apply regardless of the design procedure used. This is clarified in Section 6.1, which states that the exhaust requirements must be met regardless of whether the ventilation rate, IAQ, or natural ventilation procedure is used. This section contains a table that includes minimum exhaust rates for space types where specified contaminants are generated. Here's an excerpt from that table. The intent is to remove these contaminants at the source by exhausting them directly. For example, an art classroom in a school must be designed to exhaust 0.7 CFM per square foot of floor area. Note also that the exhaust requirements for toilet rooms are based on the number of water closets or urinals. Another nuance of this section is that the makeup air, that is the air that replaces the air being exhausted, can be comprised of outdoor air, recirculated air, or air transferred from another ventilation zone. This provides flexibility for the designer. Okay, let's turn the page now and talk about dynamic reset. Standard 62.1 explicitly permits dynamic reset of intake airflow as operating conditions change. While implementation details are sketchy, the dynamic reset option is clear. Any system control